So I'm just going to continue training. And today I'm going to review this ring buffer. Despite already have reviewed, I think it was one of the first ones that I went over with LLMs and the agents, and they verified it was correct. Actually, let me open the temporary project again. I always forget to have this other project. If it compiles, check the alarms through. So this one is used a lot. So maybe it is worth going slower, but I think I kind of already understand how it works. It's basically the same principle of an array. It kind of looks like the same thing, but then you just use a modulo or a module operator to wrap around the elements. So that's it creates a circle when adding elements. And I think this one that's the reason why there's two different styles, two different files. Because the second one is the one that is probably used most often, I would guess, which is one that grows the ring buffer when you hit the capacity. And this one, I think it just overrides the memory. Let's say you have 5 elements on the capacity, on the size of the ring buffer. Like the easiest way to imagine is like the radius of the circle would be... Actually, it's not kind of the same thing because it's more... The amount of elements is more the size of the perimeter of the circle. Maybe there's some interesting thing to do with this as well. I think the math is probably... Like it just highlights that. The way you add the memory, it follows the perimeter of the circle probably. So when you hit the limit, it's just gonna override. So if you wanna add 6 elements, then the 6th one would be overriding the first element. I think that's how it works. So initialize the capacity, pretty similar to the other ones. This one I think was used on the very first exercise, maybe on init. And I think it's something from the Snell library. Maybe I think this one is worth looking through, maybe. Because it is kind of confusing. But I think it's like something you can do when I should tell Rust that the pointer could be uninitialized, but I don't understand very well why it's used. And it could be coming from another place, probably another place. As from the memory. I'm gonna read the description again.
This is an invariant that must always be upheld, even in unsafe code. As a consequence, zero initializing a variable of reference type causes instantaneous undefined behavior, no matter whether that reference ever gets used to access memory. This is exploited by the compiler for various optimizations, such as eliding runtime checks and optimizing enum layout. Similarly, entirely uninitialized memory may have any content, while a bool must always be true or false. Hence, creating an uninitialized bool is undefined behavior. Moreover, uninitialized memory is special in that it does not have a fixed value, fixed meaning it won't change without being written to. Reading the same uninitialized byte multiple times can give different results. This makes it undefined behavior to have uninitialized data in a variable even if that variable has an integer type, which otherwise can hold any fixed bit pattern. On top of that, remember that most types have additional invariants beyond merely being considered initialized at the type level. For example, a 1 initialized vec t is considered initialized. Under the current implementation, this does not constitute a stable guarantee, because the only requirement the compiler knows about it is that the data pointer must be non-null. Creating such a vec t does not cause immediate undefined behavior, but will cause undefined behavior with most safe operations, including dropping it. Examples may be uninit t serves to enable unsafe code to deal with uninitialized data. It is a signal to the compiler indicating that the data here might not be initialized. The compiler then knows to not make any incorrect assumptions or optimizations on this code. You can think of maybe uninit t as being a bit like option t but without any of the runtime tracking and without any of the safety checks. Out pointers, you can use maybe uninit t to implement out pointers. Instead of returning data from a function, pass it a pointer to some uninitialized memory to put the result into. This can be useful when it is important for the caller to control how the memory the result is stored and gets allocated, and you want to avoid unnecessary moves. Initializing an array element by element maybe uninit t can be used to initialize a large array element by element. You can also work with partially initialized arrays, which could be found in low-level data structures. Initializing a struct field by field, you can use maybe uninit t and the end syntax to initialize structs field by field. Layout maybe uninit t is guaranteed to have the same size, alignment, and ABI as t. However, remember that a type containing a maybe uninit t is not necessarily the same layout. Rust does not in general guarantee that the fields of a foo t have the same order as a foo u, even if t and u have the same size and alignment. Furthermore, because any bit value is valid for a maybe uninit t, the compiler can't apply non-zero/niche filling optimizations, potentially resulting in a larger size. If t is FFI safe, then so is maybe uninit t. While maybe uninit is hashtag repair, transparent, indicating it guarantees the same size, alignment, and ABI as t, this does not change any of the previous caveats. Option t and option maybe uninit t may still have different sizes, and types containing a field of type t may be laid out and sized differently than if that field were maybe uninit t. Maybe uninit is a union type, and hashtag repair, transparent, on unions is unstable. See the tracking issue. Over time, the exact guarantees of hashtag repair, transparent, on unions may evolve, and maybe uninit may or may not remain hashtag repair, transparent. That said, maybe uninit t will always guarantee that it has the same size, alignment, and ABI as t. It's just that the way maybe uninit implements that guarantee may evolve. Note that even though t and maybe uninit t are ABI compatible, it is still unsound to transmute endmut t to endmut maybe uninit t and expose that to safe code because it would allow safe code to access uninitialized memory. Validity maybe uninit t has no validity requirements. Any sequence of bytes of the appropriate length, initialized or uninitialized, are a valid representation. Moving or copying a value of type maybe uninit t, i.e., performing a typed copy, will exactly preserve the contents, including the provenance, of all non-padding bytes of type t in the value's representation. Therefore, maybe uninit can be used to perform a round trip of a value from type t to type maybe uninit u then back to type t, while preserving the original value if two conditions are met. 1. Type u must have the same size as type t. 2. For all byte offsets where type u has padding, the corresponding bytes in the representation of the value must be uninitialized. For example, due to the fact that the type u size underscore of t has no padding, the following is sound for any type t and will return the original value. Note, copying a value that contains references may implicitly reorder them, causing the provenance of the returned value to differ from that of the original. This applies equally to the trivial identity function. Note, moving or copying a value whose representation has initialized bytes at byte offsets where the type has padding may lose the value of those bytes. So while the original value will be preserved, the original representation of that value as bytes may not be. Again, this applies equally to trivial underscore identity. Note, performing this round trip when type u has padding at byte offsets where the representation of the original value has initialized bytes may produce undefined behavior or a different value. For example, the following is unsound since t requires all bytes to be initialized. Conversely, the following is sound since t allows uninitialized bytes in the representation of a value, but the round trip may alter the value. Implementation source symbol t maybe uninit t 1.36.0 const 1.36 0 source pub const fn new val t maybe uninit t creates a new maybe uninit t initialized with a given value. It is safe to call assume underscore init on the return value of this function. Note that dropping a maybe uninit t will never call ts drop code. It is your responsibility to make sure t gets dropped if it got initialized. Example 1.36.0 const 1.36 0 source pub const fn uninit maybe uninit t creates a new maybe uninit t in an uninitialized state. Note that dropping a maybe uninit t will never call ts drop code. It is your responsibility to make sure t gets dropped if it got initialized. See the type level documentation for some examples. Example 1.36.0 const 1.75 sets the value of the maybe uninit t. This overwrites any previous value without dropping it, so be careful not to use this twice unless you want to skip running the destructor. For your convenience, this also returns a mutable reference to the now safely initialized contents of self. As the content is stored inside a manually drop, the destructor is not run for the inner data if the maybe uninit leaves scope without a call to assume underscore init underscore drop, or similar. Code that receives the mutable reference returned by this function needs to keep this in mind. The safety model of Rust regards leaks as safe, but they are usually still undesirable. This being said, the mutable reference behaves like any other mutable reference would, so assigning a new value to it will drop the old content. Examples: correct usage of this method. This usage of the method causes a leak. This method can be used to avoid unsafe in some cases. The example below shows a part of an implementation of a fixed-sized arena that lends out pinned references. With write, we can avoid the need to write through a raw pointer. 1.36.0 const 1.59.0 source pub const fn as underscore ptr and self asterisk const t gets a pointer to the contained value. Reading from this pointer or turning it into a reference is undefined behavior unless the maybe
So it's probably better to just ask ChatGPT. So there is just allocating based on the capacity. So the layouts is just gonna create the structure of the array. Then the alloc is gonna use that structure to actually allocate the memory and probably return the pointer of the beginning of the array. But I'm pretty sure that I already went over this once. That's why I'm remembering reading this. Then it returns the pointer as this mutable maybe underneath. There's the buffer. The buffer is equal to this, so if there is the capacity is 0, it initializes as a dangling pointer. This is one of the things that I remember that I had to change, but I don't remember what it was before this exactly. I think it was just the no null pointer or something like that. I think that this is basically explicitly saying that's going to be a null pointer. the buffer when the capacity is 0, and when you pass capacity greater than 0, then it's just gonna allocate the memory and return the pointer as this type here. Which depends on the type you initialize the ring buffer with. So here would be the item, which is the same type as the ring buffer. Then it dereferences the pointer, I think. No. I wonder, I'm not really sure what's the order of operations. Is self.write. So self.write is going to be 0 in the beginning, probably increase by 1 after each element, so it's like the writing pointer. So it's basically the same thing as the other one, the array, but instead of the array uses length to add to the pointer. And here is using write, and that makes sense. So like you need an additional pointer because it's gonna wrap around in the end. That makes sense why the vector you just add the length because it's always gonna increase linearly. But here you need the other pointer because you need to keep track of the iterations on the circular buffer. And that's the reason here. So what I think was happening is just gonna add the write to the pointer first, and it's gonna dereference that to get the actual value of the location, and then it's gonna write on that value, I think. And I assume that under the hood is gonna be using the pointer. I wonder if I can set up VS Codium to go over with the debugger. Just thought about this now. I haven't needed to use the debugger, but I haven't built anything very big yet with Rust. But so far I never used the debugger, so I'm not really sure. From VS Code you can use, in order to create the debug system, let's say, you have to use the VS Code folder. You create a VS Code folder. I think it's VS Code. Oh, it's weird here because I don't have the extension for the icons, I think. Then you create the tasks.json for, then you have to put whatever task you want to run before it runs the debugger. Like compilations, I think. You put on task.json, and then launch.json, you put the configuration of what you want to run, the actual executable. So obviously I assume that on the VS Code documentation, they probably have a template for running Rust debugger, and then the configuration would show up here. Maybe I can do this by default. Yeah, but I think that's, if I do that, I'm going to do it off string probably. But I wanted to see here, if I go over with the debugger, what's gonna be calling the write. But I'm pretty sure it's gonna be the pointer. Yeah, so here is the implementation of the maybe underneath pointer as this method. So when you dereference this here, that's what you get, because the type is the pointer to the mutable maybe underneath. So that makes sense. So dereferencing is just gonna get that maybe underneath union, I think is a union. And then it's gonna write the actual value to that place. And increase the write pointer by 1. And here is the thing that wraps around. So when you reach the capacity, just go, the pointer goes back to 0. So it means that next time you write, it's gonna overwrite the first element. Obviously not very good in some situations, I think. It just uses the new constructor to create another pointer. It references the self. So I think that is the referencing the self here, because the analog probably, I think I would expect that it lazily allocates memory. What that means is that it's kind of similar to copy on write, I think. Copy on write only copies the data when you write to it. It's kind of like a lazy load pattern. And here I think it's basically the same thing probably, I would assume. To create the layout structure, then use alloc to allocate the memory, but it doesn't allocate right away, I would assume. Just allocates the address of the pointer and probably a length or something like that, which is based on the layout here, the capacity. And then once you put the element there, that's when you're gonna initialize the value. I assume that's what's happening. So like actually, yeah, when you use the pointer, then it initializes, but maybe not. Maybe it already has the maybe underneath on this location here, and then which would be the self in this case. The self is the one that already exists on the layout, the buffer, and the pointer just moves to the location and initializes here. So it's probably what's happening. What I said is just lazy loading. If they're just the size here I saw last time as well. I was contemplating on this because on the previous exercise, ChatGPT told me to implement the DRAF, and then I tried to implement manually first, but then you need to assign the type as sized, so it knows the size at compile time, I think. But I'm not very confident if I understand what exactly does this mean here. Is initializing this struct with this type here that must satisfy the sized rate, which means that the compiler needs to know the size of the thing. I think that this however you say this symbol here, I forgot the name in English. But this basically says that P has to at least satisfy the sized rate, which means that the compiler is going to know what the size is of the element, but then I don't understand what it means. I guess kind of makes sense because the implementation is the thing that actually has the definitions of the functions, of the behavior of this thing. This is just an empty struct, and then it's going to initialize, but then what does it mean? And maybe that's because it could be, from last time I remember that these are attributes on Rust. So they are kind of like a metadata for the compiler that produces code on the LLVM level, which is the intermediate representation. So this could be adding stuff inside of the struct. Obviously, I'm not really sure, but I don't know what this notation means. So I'm gonna ask GPT, because in Rust you don't have constructors, but I think is a standard or an agreement to use the new function as a constructor. But here, obviously, I don't think that is initializing the struct with P. Like passing P as an argument is not the same thing, but maybe it is. Then, like, if it was this, you would create this weird circular thing here. Well, maybe I understand what it's saying. I think that intuitively speaking, it would be like a property, probably. Maybe it's just the type. Maybe doing this thing here is just casting the type that you pass to new, the pointer, so that it becomes the type, and then the operations know how to deal with the type. Yeah, so I think it's more of a type thing, probably. So this is why could probably be dangerous. Because if you have a dangling pointer, if the value is a dangling pointer and you reference or extract the value, then you're gonna get undefined behavior. So it's reading the stuff the 0, I think is the first element inside of the struct. So you would be the X in this case, of the 0 here, which is the P, which initializes here. Like just based on common sense, that's what I think is happening. It's like casting a type. So the class based on whatever you pass to X. And then the other are just gonna be assume that type, I think. I think I kind of get it. The operations here are going to use this value to determine what happens. Yeah, but the question is still why. I'm just going to listen to the like why use this? So why ends whether or not I'm correct about this initialization thing. I'm gonna ask GPT about this. But I think the rest of the logic is pretty simple, so it just wraps around and then increase the length by 1 when you push. And when you pop, it's just the other pointer. It's just the read pointer. So you have 2 pointers, and then they determine where, like the life cycle of the buffer. And the rest is just basically the same as an array, or the same as a vector. Because when you read, you consume the item, I think. Then increases the read pointer by 1. The length, decrease the length by 1. I'm not really sure. Intuitively it makes sense, but I'm not really sure if I get the mechanics like 100%, because it's kind of weird that you increase the read pointer as well, even though you are removing the element. So obviously the way that I naturally think about this is that the read pointer is going to assume that is starting at the end of the buffer. That's why increase, because it's from the end to the beginning. But it's kind of weird how we can use the same operation on both, because obviously they have to be symmetrical. So I think that's yeah, probably you could use the same pointer, I guess, and then just decrease instead here. So maybe this is another thing I should ask ChatGPT as well. Yeah, so this is the module thing that I was talking about. On this wraps around the index in a circle. The reason why you don't need to use this on here is because you have the cap there. Maybe if you had, I think that's the difference. Maybe you can use only one of the values and then just use the module when adding. I'm gonna ask ChatGPT about it. The rest of the implementation is very easy to understand. So those are the main questions.
T is used here because the ring buffer allocates raw memory for capacity slots, but at creation time there are 0 actual T values stored yet. Core advantage when you allocate memory for capacity elements. Those slots are just bytes. They are not initialized TS. In Rust, pretending uninitialized memory is a valid T is undefined behavior for most types. So instead of storing, the code stores, which tells Rust, this memory may or may not currently contain a valid T. That matches exactly how ring buffer works. Some slots contain real values, some slots are empty / uninitialized values are written later, values are removed later. Why not allocate T directly? If you used, then Rust assumes every slot contains a valid initialized T. That would be wrong immediately after new, because no elements were constructed yet. Example, you definitely do not want 100 fake uninitialized string S sitting there. Why maybe uninit specifically? It allows 1 allocate memory without constructing values, no constructors run. 2 write values later when pushing. This initializes 1 slot. 3. Read values out later safely when popping. This moves the T out. For avoid dropping empty slots, only initialized elements should be dropped when buffer is destroyed. Why is it a union? Internally, maybe uninit T is implemented roughly like a union means. Same memory can be interpreted in multiple ways. Compiler does not assume the T is valid, yet that is perfect for deferred initialization. You can think of it as raw storage large enough for T, with no promise it contains a real T. When is it used? Use maybe uninit T whenever memory exists before initialization. Common cases: collections, vector ring buffers, arena slab allocators, erase initialized element by element FFI out pointer C function writes into provided memory. Performance sensitive code avoid initializing memory twice. In your ring buffer at new, so all slots are uninitialized. After pushes, after pops, those slots become uninitialized again. That life cycle is exactly what maybe uninit is for. Short version: the advantage is it lets the ring buffer own memory for capacity items without requiring all capacity items to be valid TS immediately. Without it, you need dummy values option T overhead UB extra initialization cost important mental model maybe uninit T is not for nullable T. It is for bytes reserved for a future T. In one sentence, this ring buffer uses maybe uninit T because capacity memory exists before elements do.
Yeah, so it's basically exactly the thing that I was talking about. That it works like a lazy loader type of thing. So I think normally what GPT is saying is that normally if you don't use maybe an init, then Rust requires you have the values before initializing the memory. But then here with maybe an init, it allows you to have the memory without necessarily having the values. But then that can be dangerous because you can create dangling pointers. I think that's what it means. But the reason why it's better is because it allows you to do this lazy loading type of thing, where it only initializes the value the moment you're gonna use it. But I still don't understand very well why specifically on circular buffer that matters. I think it's just like a small optimization probably. Yo, what's up? I think it's just because you're gonna reuse the memory. But even then, it's kind of weird because in some situations, because it's basically the same thing, I think, on a vector. Like, trying to think what is the best way to think about this. I'm reviewing the solutions I have on this list here, this massive list. Like the idea is I have a folder with exercises and a folder with solutions. But the main goal is to become very good at Rust. But then the challenge is that like doing quizzes on websites is not very high density. And if I just try to build projects, I'm gonna default to using agents or stuff like that, which makes me plateau on a certain level. So I did these two things to try to force myself to actually code, and not necessarily code, but just think for myself on how to build everything. So there's a folder that I use agents to build a bunch of exercises of. So first, I researched the fundamental data structures in Rust, the data structures that I'm probably going to use all the time to build things. Then I use agents to build a bunch of the exercises and the solutions. Then I use I did another pass with an agent as well, and LLMs to review the solutions to see if they are correct. But then obviously I'm not 100% sure. So what I'm doing right now is just going over all of them one by one to manually verify for myself to see if I think it is correct or not, and then using LLMs to help and looking at the documentation. It's kind of like already an exercise on itself. But then once I'm done reviewing all of them, the idea is to go over the solution one by one, and the exercise one by one. And the exercise is that you have to re-implement parts of the solution on your own. I think there are scripts here as well that the agents created that you use, and I think the scripts use cargo watch, and they basically allow you to like incrementally do the exercise. I'm not sure. I think that there are scripts that randomly select. Yeah, so this script selects one of the exercises I should do randomly, and I think the run allows you to run this one. I don't remember. Yeah, so basically it's gonna compile, it's gonna watch the file. It compiles every time you make a change and you save, and the goal is to reconstruct the solution. So once I'm done reviewing all the solutions, I'm gonna try to keep a habit or a ritual of doing this every day. Then I did the other site that I did is a Rust Forge Gym, which is a website. I started with some parts of the parser from the Rust Quiz website, and then I had agents as well to do this. And it's basically a site that has a bunch of quizzes that test like fundamental parts of whatever is needed to build things. Like the main thing that I hate about the other stuff is that is not like lead code challenges and stuff like that. It feels like a waste of time because you're solving things that don't actually matter for building stuff, and what I care about is building stuff. So I'm trying to only have quizzes of stuff that is gonna be high density and high value to build things. And I'm basically trying to do this as a ritual. So there's this other site here. This is the one that I got. They have a free GitHub repo that uses Rust to produces these quizzes here. Just I got the parser from them, and then I built this simple website for myself. And the quizzes on this site here are very good. And I just converted some additional ones from the Rust book, and I'm thinking about creating extra ones as well, depending on what kinds of things I find that are very interesting to do, or to train, to understand. I don't talk about my personal life on stream. So, how can I ask this? I'm gonna ask this one first, then I'm gonna ask the one about this.
Yes, this is also true for VecT internally. In fact, VecT is one of the classic examples of where maybe unint or equivalent raw memory techniques are needed. The key distinction is, user-facing VecT API makes it look like every element exists normally. Internally, a VecT manages allocated capacity separately from initialized length. That same separation is what your ring buffer is doing. The three different concepts for a VecT or ring buffer, there are really three things. Allocated memory equals enough bytes for NTS initialized elements equals actual valid T values currently living their logical metadata equals length. Read/write indexes, etc. Example. At that moment, memory for ATS reserved length equals 00 actual TS exists at that. Memory is just raw bytes. Why this matters, Rust types are not just bytes. Example, these types have invariants. Random bytes are not a valid string. So if Rust believed your raw capacity memory already contained 8 string S, disaster would happen. Under the hood without maybe uninit, suppose you allocate room for 4 string S. Memory returned by allocator might contain garbage. If treated as string, Rust assumes each slot contains, but those numbers are garbage. Then if dropped, Rust tries to free some random pointer right where arrow UB /crash/corruption. With maybe uninit string, now memory is interpreted as Rust understands. This memory may not contain valid string s yet, so no destructor runs automatically. No reads allowed as string. Just draw storage later. Now slot I truly contains a valid string. Important insight: values living in memory. This is subtle but central. In Rust/C++ style languages, memory and objects are different things. You can have raw memory with no object, memory containing a live string, memory where object was removed. Maybe uninit t is the tool for representing this life cycle safely. Y vectors needed to when pushing internally. Find next free slot in allocated memory. Write x their increment length. Only first len elements are initialized. Remaining capacity is uninitialized storage. Y ring buffers emphasize it more. A ring buffer has holes over time. Example: capacity 5, pop 2, push T, push F wraps around, push T. So initialized slots move around non-contiguously. That makes explicit uninitialized slot handling more obvious. Why not just use option T? You could, then empty slots are none. But that means every slot initialized upfront, maybe extra memory, extra branching / tag checks constructing and values initially. Maybe uninit t avoids that. Deep under the hood summary without maybe uninit Rust assumes every slot is always a valid T. That means reading aloud dropping expected reference is allowed dangerous if false. With maybe uninit Rust assumes nothing. That means, nope, this is also true for vec_t internally. In fact, vec_t is one of the classic examples of where maybe uninit t, or equivalent raw memory techniques, are needed. The key distinction is, user-facing vec_t API makes it look like every element exists normally. Internally, a vec_t manages allocated capacity separately from initialized length. That same separation is what your ring buffer is doing. The three different concepts for a vec_t or ring buffer: there are really three things. Allocated memory equals enough bytes for NTS initialized elements equals actual valid T values currently living their logical metadata equals length. Read/write indexes, etc. Example: at that moment, memory for ATS reserved length equals 00 actual TS exists that memory is just raw bytes. Why this matters: Rust types are not just bytes. Example: these types have invariants. Random bytes are not a valid string. So if Rust believed your raw capacity memory already contained 8 string S, disaster would happen. Under the hood without maybe uninit, suppose you allocate room for 4 string S. Memory returned by allocator might contain garbage. If treated as string, Rust assumes each slot contains, but those numbers are garbage. Then if dropped, Rust tries to free some random pointer rightward arrow UB/crash/corruption. With maybe uninit string, now memory is interpreted as Rust understands. This memory may not contain valid string S yet, so no destructor runs automatically. No reads allowed as string. Just draw storage later. Now slot I truly contains a valid string. Important insight: values living in memory. This is subtle but central. In Rust/C++ style languages, memory and objects are different things. You can have raw memory with no object, memory containing a live string, memory where object was removed. Maybe uninit t is the tool for representing this life cycle safely. Y vectors needed to when pushing internally. Find next free slot in allocated memory. Write x their increment length. Only first len elements are initialized. Remaining capacity is uninitialized storage. Y ring buffers emphasize it more. A ring buffer has holes over time. Example: capacity 5, pop 2, push T, push F wraps around, push T. So initialized slots move around non-contiguously. That makes explicit uninitialized slot handling more obvious. Why not just use option T? You could, then empty slots are none. But that means every slot initialized upfront, maybe extra memory, extra branching / tag checks constructing and values initially. Maybe uninit t avoids that. Deep under the hood summary without maybe uninit Rust assumes every slot is always a valid T. That means reading aloud dropping expected reference is allowed dangerous if false. With maybe uninit Rust assumes nothing. That means no accidental drops, no invalid reads, explicit initialization, explicit destruction, exactly what the level containers need. One sentence mental model: vec_t capacity memory and ring buffer slots are parking spaces. Maybe uninit t means parking spaces exist, but cars may or may not be parked there. Regular t means every parking space must already contain a real car. Final answer to your question: yes, vectors absolutely have the same issue. The difference is that vec_t hides it behind a safe API, while your ring buffer implementation exposes the low-level mechanics directly.
Yeah, so I think I understand. So if you don't have the maybe uninit, you would try to drop the memory. And then you could cause crashes because you are dropping a place of memory that may or may not exist or might be out of bounds or whatever. So the next question is, what happens here? I think the rest of this stuff is probably not worth it to dive into right now because, like I said on the other time, I think it's probably better to just go over, to just take one time to go over to everything in depth. All these attributes here, I'm gonna have to study the Rust compiler to truly understand how this works and the definition of some of the functions or some of the traits, some of the stuff that I can see here. So I'm just gonna not gonna care about this now, I think. The rest of this is like pretty much very simple. It's very similar to the other ones. So I think I'm just gonna go over to the next exercise. This is already marked as checked. So I'm gonna go to this one, which basically the same as the other one, but probably different when on the push and pop, because this one is gonna grow the buffer instead of just wrapping around. But there was another question that well, I was gonna ask about so maybe before I go, like right off the bat, this seems kind of weird because it seems like exactly the same as the other one. But I remember that I was gonna ask, what if I only had one pointer? And why not have one pointer if the operations are the same and they are symmetrical? I'm gonna ask that next.
What you're seeing is not a constructor call and not related to the attributes. It is the definition of a tuple struct. Means, define a struct type named maybe dangling with one unnamed field whose type is p. This syntax often surprises people coming from C++ because it looks like function parameters. What this means exactly, it is roughly equivalent to a normal name field struct. That syntax isn't legal Rust, but conceptually it's field 0. More practically, it's equivalent to, except the field has no name, only an index. Tuple struct syntax Rust has 3 common struct forms. 1 name fields uses, 2 tuple structs uses, 3 unit structs no fields. So yours is simply a one field tuple struct, sometimes called a new type wrapper. What is p here? P is a generic type parameter. Means p can be any type, even dynamically sized ones. Sized, like stru8 trait objects then inside, means the field type is p. So examples, why does constructor code look like this? Inside, this does construct a value. Because tuple structs have constructor syntax matching their shape. So, means, create a maybe dangling whose field 0 contains x exactly like, coming from C++ mental model C++, Rust tuple struct, very similar idea, just compact syntax. Then construction is analogous to, why use tuple struct instead of name field? Usually for new types, wrapping another type to give it different semantics. Examples, this gives 0 runtime overhead distinct type custom trait and please control APIs why and maybe dangling specifically. It wraps some pointer slash reference like type p, but changes the semantic meaning. Treat this pointer as allowed to dangle. So instead of using raw p, they create a distinct wrapper type. About the attributes, hashtag repair, transparent, very important here. Means, layout of maybe dangling p is exactly the same as p, so has same memory representation as asterisk mut t. No overhead. Useful for FFI and compiler guarantees. Hashtag derive, auto implements traits like debug copy clone default hashtag rust underscore pub underscore transparent internal compiler attribute, not normal user Rust. Mostly implementation slash compiler plumbing. Not related to tuple syntax. Concrete example field access. So for maybe dangling, stores PTR in field 0. Important subtlety, size this allows, which means the last field can be unsized, because tuple structs can have DST last field. Final mental model means, create a new wrapper type named maybe dangling containing exactly one value of type p. It is type definition syntax, not function call syntax. And later is the constructor expression for that tuple struct.
My back is kind of fucked from sitting on this chair. I was gonna ask about the pointers. 2 pointers. Buffer. I'm looking into the exercise here. Oh, maybe that's why it felt weird there. But it is the same thing here. The difference here is that no, but I think it's basically the same implementation as the other one. Well, maybe the difference is probably this one. So everything else is the same, but this one has this growth function. I think that's the difference. Compile here. I saw the growth function here. Length has reached capacity. Useful. It's basically exactly the same as the other one, just as this function. And this is something that I think that it could be improved if I remember correctly. I think I roughly, like I superficially went over this, I think, on time, but maybe I didn't and I just remember. But I think whenever you are multiplying something like this, you can use the checked view, I think, or something like that. Check that. No, check this one. And then you just do there. So I wonder why on the option. Maybe it's like unwrap or then 0. I think that's the way you should do it. Then you probably remove this because it's not necessary. Actually, it should be 1 here, I think. Oh, not really sure though. Before I change, I'm gonna ask ChatGPT, but I think that's so. The better way would be to just remove this and then just leave it like the way that I'm doing now. So what this does is safely multiply the capacity by 2, and then if you can't do it, then it's just gonna be 1. It's basically, I think it is the same as the other thing was doing, but it's a better pattern because it checks for the overflow. Or whatever. Then it creates the layout based on new capacity, allocates the buffer. This one I saw on other implementations as well, but I don't think I'm gonna maybe just superficially look into this. I think I already looked into this on the last time as well. I assume what is happening is just gonna copy, like it says, copy and not overlap. But obviously I'm not really sure what it means because I don't know the full implementation. Maybe this is the one. Yeah, whatever. Maybe you can ask ChatGPT as well to clarify what this does, but I think it just copies like it says there. Gonna copy from the source to the destination and by this amount. So the read should be at the tail of the buffer. So at the end of the buffer, it's gonna move the buffer pointer to the end here as the source. The destination is gonna be the new capacity. Yeah, that makes sense. So it doubles the capacity, then it's gonna get the pointer to the new destination, the new end, and then it's gonna move the read pointer to the new end. That's what's happening here. Pretty sure. If the read is smaller than the write. Contiguous read and write. Not, it just wraps around. Because it goes on a circle, obviously. But I think that this check is just because you're dealing with probably unsigned numbers. Yeah. So unsigned size. So it means it's gonna be positive, so this is gonna wrap around. Sometimes the read's gonna be bigger than the write. So I have to wrap around. Get the tail here is basically the same thing, I think. Yeah, so you get the tail based on this delta difference between the capacity and the read. Then just move the read pointer to that place. But here's moving the write as well. Maybe I should ask GPT about this. But here, here's moving from the original buffer, and here so I think I'm just gonna ask in general first to see what it thinks, and if there are any mistakes or things that could be improved, and then I'll dive deeper into this so that it explains how does this work and why does it do this. I think I have a rough idea. I think it's gonna say that I should improve this probably. But maybe not.
Yes, you're asking exactly the right design questions. This gets into why ring buffers usually use two indices instead of one, and how wraparound is optimized. Why not use one pointer only? You proposed push, moves pointer forward, pop, moves pointer backward. That sounds symmetric, but it changes the data structure semantics. A Q/ring buffer is usually FIFO, first in, first out. That means push writes at the tail, pop reads from the head. Those are two different moving positions. So ring buffers usually track. Example with 2 pointers, capacity equals 5 start, push ABC, pop 1, remove A, push D. Everything works because read moves independently, write moves independently. What if you used one pointer? Suppose one pointer key. If push increments key and pop decrements key, then pop removes the most recently added item. That becomes a stack, LIFO, behavior, but Q needs. So one pointer with opposite movement gives stack semantics, not Q semantics. Could one pointer still work somehow? Yes, but you need extra state. Examples: option A, 1 pointer plus length plus infer head / tail, mathematically possible, but more complicated. Option B, 1 pointer plus generation counter plus occupancy bitmap, possible, but over-engineered. Practical reality, 2 indices is simplest and fastest. Why 2 pointers are natural? Because Q has 2 ends, just like a decline. Why no % capacity? You noticed wraparound done like, instead of, yes, usually for performance and simplicity. Percent can be more expensive. Modulo involves division-like instructions on many CPUs, whereas is often cheaper and branch predictable, especially in tight loops. Why branch is often good here if capacity is large. Wraparound happens rarely, so CPU predicts, usually false. Very cheap. Example: capacity equals 1024 for 1023 pushes, then once. Great for branch prediction. Power of 2 optimization. Some ring buffers choose capacity equals power of 2 and use instead of modulo. Example: cap equals 8. Very fast bitmask wraparound. Why fixed size ring buffers often use this style? Since yours is educational / fixed capacity is readable and efficient. Why not decrement pointer for pop? Another subtle issue: pop does not mean undo last push. It means remove oldest unread item. So read pointer advances forward through time too. Both read and write often move in same direction. They chase each other around the ring. Visual intuition: think of a circular conveyor belt. Right pointer equals place new boxes onto belt. Read pointer equals remove oldest box from belt. Both stations fixed conceptually, but indices move around ring. Final answer: why not one pointer? Because one pointer with push forward / pop backward gives stack behavior, not Q behavior. FIFO needs 2 independent positions, head and tail. Why no %? Because is often faster and simpler than modulo, especially in hot code. One extra note: many ring buffers also keep len, because with only read / write indices could mean either. Empty full, so len disambiguates the cleanly. You're asking exactly the questions implementers ask when you review the growing ring buffer next. You'll likely see another challenge: how to relay out wrap data when resizing. That's where ring buffers get really interesting.
I kind of get it, but still kind of confusing. I understand the concept level. I understand what it's saying. It's difficult to imagine in practice, like what is going on with the data. Because obviously, if you have one pointer, like it says there, you remove, you're gonna get the stack behavior. It's like pushing and popping instead of the stack. Just when you push, you increment the pointer, and when you pop, the increment. But then if you use the math like it says there, then you could emulate or basically do the same thing as with 2 pointers. Yeah, this is what I was thinking about. It's kind of complicated to think about. Yeah. So yeah, this makes sense because this would be like the same thing. Because you're just doing operations with addresses either way, so that's what I was thinking. But the way that I was thinking is that the functions would be like the mirror of each other, obviously. So I'm not really sure if that's the case on this situation, but I think it must be. But maybe not. Maybe it's saying that they have to be the same. Because if they are 2 different pointers, then it's just gonna be like it's the same thing, but you just do like you keep track of the other pointer with math by calculating the difference with the length. So assume is implying that the functions would be the same. But the question then would be why. I think the reason why is because of the stack thing. If they are the mirror of each other, they become a stack. Because then for each push, you have the pop and just flows based on the stack pattern. But if the functions are the same, then it wraps around based on the calculation. Try to visualize on my mind what that looks like. It's kind of hard to grasp, I think. This is the weird thing because here is 0 as well. So it's always gonna pop from the beginning. Yeah, that's what it means. It pops from the beginning so that you have the queue behavior. Because if it pops from the end, then you have a stack. That's what it's saying. I think that like the map is kind of confusing because we thought about the same thing but in different ways. Because I think another way would be to make the read equal to the length in the constructor and then decrease. But then that would be the stack behavior I think that he was talking about. That's kind of confusing. Like it's easy to understand this implementation, but it's confusing. I'm spending more time here because I wanna like there is something here that is deeper that I'm trying to think about this whole symmetry thing. That's the thing that I'm curious about. 'Cause I think if I understand that, then it's gonna allow me to. It's gonna make it easier to implement this from scratch, or implement variations of this in the future. Like there's two different variables. There's the amount of pointers you have, and then there's the sign of the operation, so the movement of the pointer. I think that's the thing that I'm thinking about. Maybe I'm gonna ask because this is like more of not philosophical but mathematical question, I think. But I'm gonna ask this. When I ask first about the implementation of the growing ring buffer, I'm gonna ask what it thinks. Then I'll ask this deeper question I'm more curious about. The thing that I'm thinking about is that you have like you have two variables. You have the amounts, the number of pointers, and you have the sign of the operation. And what I'm thinking about is what fundamentally changes by changing the variables.
Yes, this is actually a solid study implementation. It demonstrates the important mechanics of a manually managed growing ring buffer. Raw allocation may be done in a TF-IFO semantics wraparound growth when full preserving logical order during resize correct destruction of remaining elements for a study exercise. It is definitely good enough and mostly correct. That said, there are some things worth discussing: correctness, safety, style, and possible improvements. High-level verdict: good news. I do not see an obvious logic bug in normal use. Your tests cover normal push/pop grow preserving order grow after wraparound multiple growth drop behavior 0 capacity. That's excellent coverage for a learning exercise. The strongest part, grow. This is the heart of the structure, and it is well done. When full, you allocate a bigger buffer and copy elements into, then reset. That is exactly the cleanest resizing strategy. Important subtle correctness point. Move vs copy you use, on maybe uninit T slots. This is okay here because you are moving raw bytes of initialized T old buffer is deallocated without dropping elements. Again, new buffer becomes owner of those values, so no double drop occurs. That's valid ownership transfer at raw memory level. One thing I would improve immediately, pop, current code. This works, but is awkward. Better, or why? Because your version creates a reference MT then copies / moves from that reference cleaner is to directly move out of maybe uninit T. Recommend.
I don't feel like thinking about this too much here. My mind's more on the other stuff now. But I guess it makes sense what it's saying. It's gonna depend on the difference between these two here. So this one assumes that the reference was initialized. Not sure though. And then it reads the reference with a pointer. This one adds the read pointer to the buffer, then reads that, and then it assumes it was initialized. Yeah, whatever.
T. Recommended. That exists for exactly this case. Another improvement. Use dangling pointer instead of null and new. 0. You do. That works because you guard accesses. But standard library style prefers. Why? Because some APIs and optimizers prefer pointers to be non-null even if never defer-ranked. It avoids null special casing. So not required, but cleaner. Potential overflow issue in grow. Could overflow usize. Then weird behavior. Safer. This matters in production. Less in study code. Drop implementation. Good. But oh, and
Yeah.
you do. This is logically correct and elegant.
So it's basically saying almost exactly what I said there before, but it uses the expect instead. And I was using the unwrap or.
Each remaining item gets dropped exactly once. Could be optimized by directly iterating initialized slots and calling drop underscore in underscore place, but for study purposes your version is nice and clear. One subtle concern, panic safety during grow. Suppose allocation succeeds, then copying partially happens, then panic occurs. Unlikely here since copy itself doesn't panic. Since raw pointer ops don't panic normally, you're okay. So no real issue in this version. Performance notes growth strategy doubling excellent. Gives amortized 1, push. Copy on grow expected. Wrap checks good. Missing ergonomics, fine for study. Could add, peak, clear, iter, reserve, is underscore full. Maybe less relevant once growable front, /back, but not necessary. If I were grading this as a study exercise correctness, 8.5/10 very good. Demonstrates understanding. 10 you clearly understand. Allocation ring indexing ownership resizing logic production readiness. 6 needs. Non-null more safety comments check growth unsafe encapsulation cleanup perhaps allocator support 2 best improvements to make now 1. Replace pop, body use, 2. Replace growth calculation 1 advanced subtlety. After moving during grow after copying bytes from old buffer to new buffer. Old memory still contains byte patterns of old values. But since you deallocate old memory without dropping them, and only new buffer is considered owner, that's okay. This is an important low-level concept many beginners miss. Final verdict for your exercise. Yes, this is a good solution. It is conceptually correct and teaches the right things. If your goal is learning, excellent example. If your goal were shipping a library, needs polishing, but foundation is solid. My honest opinion, this is much better than many beginner unsafe Rust data structure implementations because it respects ownership and drops semantics. That means whoever wrote / reconstructed it likely understands what they're doing. If you'd like, I can also show you how the standard library vector solves growth differently, and why it avoids the full unroll copy in some cases.
So I'm much more curious about this thing here. So I'm just gonna spend some time talking about this with ChatGPT and probably do some quizzes and stop streaming. And I think I'm gonna spend a little bit more time reviewing the big solution there to see if I can improve it with ChatGPT, probably on another chat thread. I think I'm gonna use other LLMs as well to review this one. Because ring buffer, I know, like ring buffer or variations of ring buffers are used all the time. So based on my experience with other languages and other stuff that I want to build, I think the 3 things that I use or I've seen the most on stuff that actually matters is graphs, trees, and queues. Those 3 I think are the most useful ones. And like one of the main patterns is virtualization. So obviously virtualization, you have the DOM tree, and then you want to create a queue on the DOM tree. So the main pattern is translating the tree into a queue and translating the queue into a tree. So this pattern I think is very important. So it's probably the one that I'm going to spend the most amount of time. And also on the kernel, you have the queue to receive requests. It's also a circular queue or circular buffer, however you want to say that. I think that this is very important. Then graphs, obviously, for machine learning stuff. When I ask this fundamental question here about this stuff, more like abstract stuff, I think. The main thing that is changing is the pointers and the movements of the pointer on this shoe. I think when it comes to circular or ring buffers or circular queues, like these kinds of things, I usually struggle to think about them on my mind of what's happening with the data on runtime. I think it's just confusing because like you can overwrite the same place in memory. It's kind of weird because you have the length and you have the two different pointers. It's kind of difficult to intuitively think about. Because the problem is like imagining all the edge cases that can happen on runtime. I think that's what I struggle with. And also because in most situations you're not only gonna have that data structure, you're gonna have a much bigger, more complex thing that you need to solve, which usually is gonna force side effects and stuff like that.
Yes, you're touching a deep structural way to think about data structures. Many linear data structures differ less by what they store and more by how positions move and how many active endpoints exist. That's a very powerful mental model. Your two variables you identified, number of pointers / indices / cursors sign, direction of movement for operations we can refine this slightly into, number of mutable positions which operations move which positions, direction of movement access policy, FIFO / LIFO / random / etc. Whether storage is linear or circular, those variables generate many common structures. Is the stack vs queue distinction just sign? Short answer, almost, but not completely. A stack and queue can use similar storage, but differ in which end each operation uses. Example, one array, one moving top pointer stack same pointer, opposite direction. Result, newest item removed first. So yes, sign reversal on same pointer strongly characterizes stack behavior. Queue/ring buffer two positions, same direction. Result, oldest item removed first. So yes, adding a second independent pointer fundamentally changes semantics. So your insight is correct. Stack vs queue can be viewed as cursor motion differences. That is an excellent systems level perspective. But not only sign, because what matters is also whether push/pop share same pointer, whether read/write pointers are distinct, whether movement wraps, whether access is constrained. So sign is one variable among several. Taxonomy by pointer motion 1. Stack storage plus one pointer, meaning insert/remove same end LIFO 2. Q 2 pointers, FIFO 3. Ring buffer Q plus circular indexing. 2 pointers, FIFO with fixed capacity or growable circular storage. 4 dict 2 ends available. Now you have two logical endpoints, both mutable. Very flexible. 5 priority Q/heap movement isn't linear cursor motion anymore. Instead, motion governed by ordering invariant. 6 linked list pointers are per node, not array indices. Operations move references through graph topology. Another deep variable, endpoint symmetry ask, where can insertion happen? One end only rightward arrow stack/q both ends rightward arrow dict anywhere rightward arrow vector/list where can removal happen? Same end is insert rightward arrow stack opposite end rightward arrow q both ends rightward arrow dict that often matters more than sign itself. Why stack equals same pointer opposite sign because stack keeps one frontier, push expands frontier, pop contracts frontier. Same boundary, opposite motion. Why q equals two frontiers, same sign q has two boundaries. Tail advances as items added. Head advances as items removed. Both move forward through time. Movement through time intuition, very useful concept. Stack you undo recent history. Q you consume history in arrival order. That's why pointer motion differs. Other transformations by changing your variables same storage. Change endpoints. Vector plus restrict offs. Only push/pop and rightward arrow stack push and/pop front rightward arrow q. Slow and less ring buffer. Both ends rightward arrow dict same 2 pointers. Change over right policy. Ring buffer full. Reject push when full grow buffer over right oldest item 3 different structures/semantics. Same queue, change scheduling. FIFO queue priority queue randomized queue storage may look similar. Policy changes semantics. A generalized model think of data structures is examples. Stacked queue heap. So is your statement correct? The fundamental difference between stack and ring buffer is pointer movement. Yes, in a meaningful implementation sense. More precisely, stack, one frontier, opposite movement for push/pop q/ring, two frontiers, same direction advancement. That's an excellent abstraction. Even deeper insight, many algorithms are just state machines over indices. Data structures often emerge from number of indices, update equations, invariants. That's exactly how experts design new structures. If you enjoy this way of thinking. Next natural step is comparing. Stack allocator, arena allocator, free list, slab allocator, dict, work stealing, dict all can be understood as pointer motion systems. Final summary, yes, you're discovering that many data structures are fundamentally defined by cursor topology and movement rules, not by mysterious categories. Changing number of pointers which operations move them, direction wrap around endpoint permissions can transform. Stack queue ring buffer dict heap like schedulers allocators. That's a very advanced and correct way to think about them.
So the other thing I want to ask is about the other data structures, because I think the other fundamental variable is going to be space.
Yes, this is a very powerful abstraction, and you're moving toward how systems researchers often think. Data structures are not named boxes. They are rules for navigating and organizing memory. Your third variable, space, is real, but it needs refinement. Your three variables, refined, you proposed, pointers sign slash movement space that's close. I formalize them as 1. State variables slash cursors indices, pointers, handles, roots, counters. 2 transition rules how operations update those variables. Examples, top plus equals 1 head equals head dot next equals hash, k. 3. Memory topology how elements are laid out and connected. Contiguous array circular array link nodes tree graph buckets plus chains skip levels pages slash blocks this is what you mean by space. That is absolutely a legitimate deep framework. Is a tree a queue fragmented in space? Short answer, not exactly. Interesting intuition, but not precise. A queue preserves linear temporal order, one next item. A tree preserves branching hierarchical relationships, multiple possible next nodes. So the difference is not only fragmented space, but branching topology. Better statement, a tree is a linked structure whose topology is hierarchical rather than linear, whereas queue slash list are linked structures whose topology is sequential. That's the key distinction. What is stack plus space? Great question. Equivalent of stack in non-contiguous memory could be linked stack each push allocates node, push, pop. This is literally stack semantics on fragmented space. So, array stack equals contiguous topology, linked stack equals node topology, same abstract structure, different memory topology. This is an important realization. Abstract data structure vs concrete representation stack, abstract behavior. Push pop LIFO can be implemented with array linked list segmented blocks, persistent tree nodes, same ADT, different topology. Hash map in your framework, yes. Hash map is excellent example. You said hash function connects separate addresses exactly. Topology is memory navigation is computed, not sequential. That's a major topology type. So are all data structures combinations of these variables? Broadly, yes. A strong generalized model is your 3 variables map well to first 3. Need to add 4. Invariance slash constraints examples. Heap property BST ordering load factor sortedness uniqueness without invariance. Many structures lose identity. Spectrum of common structures 1. Vector slash dynamic array pointer slash state base pointer len cap movement dependent end index arithmetic space contiguous invariant initialized prefix 0 len 2. Stack state top or len movement push plus pop space contiguous or linked invariant LIFO frontier 3. Q state head slash tail movement in Q tail forward deck Q head forward space link for circular array invariant FIFO order 4. Ring buffer state read slash right slash len movement both cursors advance wrap around space circular contiguous array invariant modulo indexing 5. Linked list state head slash tail slash current movement follow next slash previous pointer space fragmented nodes invariant chain consistency 6. Tree BST slash AVL slash etc. State root traversal cursor movement left slash right descent rotation space fragmented graph nodes invariant hierarchical edges ordering slash balance rule 7. Heap slash priority Q state array plus count movement sift up slash down space contiguous but interpreted as tree invariant parent priority dominates child. This one is important. Tree topology can be virtual, not physically linked. 8. Hash map state bucket array count movement hash key probe or chain traversal space array plus fragmented nodes or open address table invariant keys reachable from hash bucket 9. Graph state vertices plus traversal frontier movement follow adjacency edges space arbitrary topology invariant edge relations deep insight. Topology can be physical or logical example heap. Memory is contiguous, but logically. So space can mean physical topology actual addresses. Logical topology relationship induced by indexing slash pointers. Both matter. Where your model becomes very strong, you can classify almost anything by asking, how do I find next element? Increment index follow pointer hash compute compare key and branch pop frontier. What memory pattern does that imply? Cache friendly contiguous pointer chasing random access branchy tree walks that predicts performance. Example, y arrays fast, trees slower same big O maybe O, log n, VSO, 1, indexing, but arrays equals local cache lines trees equals random nodes plus branches that's topology cost. Final refinement of your framework use this 4-part model that can describe most useful structures. Final answer to your specific question is a tree a queue fragmented in space. Not quite. Better, a queue is a linear traversal topology, a tree is a branching traversal topology. Both may use fragmented memory. What is stack plus space? A linked stack, nodes instead of array slots. My honest opinion, you are thinking at a data structure designer level, not beginner level. You're abstracting beneath names into state movement topology. That's exactly how new structures are invented.
And we're just gonna do like 1 or 2 quizzes, I think. Still haven't changed, so it's probably gonna be, or maybe it's not. Maybe it is picking up random quizzes. I don't remember seeing this one on the last time that I did this. I think this is an error. So it's initializing here, which is kind of weird already. And maybe this is acceptable. Like this has to be an error because this is not mute, and then it's assigning here. I'm not really sure if you can do this in Rust where you don't assign to a value. I think you probably can't. Now b equals false. Actually, maybe this one is a tricky one. Yeah, because I think that the lesson this one is that's gonna run here either way. Like it doesn't matter that it's always false. From the compiler point of view, it's gonna check this. I think it's an error. Yeah.
Explanation because S could be moved inside of the if statement. It is illegal to use it on line 8. While the if statement will never execute in this program because B is always false, Rust does not in general try to determine whether if statements will or won't execute. Rust just assumes that it might be executed, and therefore S might be moved. Back.
Yeah, so that's the last one on this one, I think. This one, I remember I did this off stream, I think, yesterday. And the lesson here is that map on Rust is lazy loaded. So it doesn't run the moment you do this thing here. Which I think in JavaScript you would run the map and then you would, I think, copy the map on this variable here. But in Rust it doesn't do that. So it's only gonna run when it's here. But I think I got the answer wrong on this last time. I think it's gonna be 1 for the first output. It's module 2. And I think that's the thing that I'm not really sure about. Because 1 divided by 2 is obviously 0.5. I don't remember how module works very well. I think it's just gonna be 1. Because it doesn't divide, so it's 1 and 1. Then 2 and 0. And then 3 and 1. I think that's the answer. Yeah, nice.
As described in the documentation of the iterator map method, the map operation is performed lazily. The closure provided as an argument to map is only invoked as values are consumed from the resulting iterator. The closure is not applied eagerly to the entire input stream up front. In this code, the for loop is what drives the iteration. For each element consumed from the parity iterator, our closure needs to be evaluated one time. Thus, the output will alternate between numbers printed by the closure and numbers printed by the loop body. Back.
It is kind of weird. I think it's gonna be 1, obviously. And the question is whether or not it drops. No, I think that doesn't make sense. Like, it's gonna be 1. It's gonna be 1, and the other one's gonna be 2. Not really sure though. Because the problem here is that, like, you're creating a pointer, I think. I think this creates a pointer, but I'm also not sure. Because they're not using clone. I think in Rust, if you wanna clone the value, you have to call the clone method. So in my mind, this variable here is a reference to this other one. So it just points to this location in memory. But I'm gonna ask this to GPT. I think I'm not gonna ask. I'm gonna ask offstream because I wanna continue on the same thread there. But I think here is basically, yeah, but then maybe for a string is different. Yeah, not sure. I'm just gonna guess.
RustForge Gym Home Dashboard Start Session I32 can be used after assignment, but string cannot. Explanation: this program demonstrates Rust's smooth semantics and copy types invariant. Types that implement the copy trait, like all primitives, I32, bool, char, tuples of copy types, etc., are implicitly copied on assignment or when passed by value. The original binding remains fully usable. Non-copy types, like string, vectee, structs containing non-copy fields, etc., are moved by default. The original binding is invalidated. This is what prevents use after free bugs. Valid example, copy type invalid example, non-copy type. The compiler enforces this rule automatically. This is why you sometimes need clone, expensive, or borrowing, empty, when you want to keep the original value. This invariant is one of the foundations of Rust's ownership system and is the reason you see use of moved value errors so often when learning the language. Back home, try again next quiz.
So that makes sense. That's the reason why I have this quiz. So on some built-in types, it's gonna copy by default because it implements this copy trait. Then the copy trait kind of like overrides the compiler operator semantics, I think. And it allows you to copy the value for these simple built-in types. But then for a string, you're gonna move the value, so you're gonna get the reference on the B, I think. Maybe don't get the reference, maybe get, yeah, I think you don't get the reference, you just own the value. Yeah, so it moves. So if you would use the S, so you don't get the reference, it actually gives the ownership of the value to the other variable. So the S1 becomes useless after that. That's how it works. Yeah, so I'm gonna continue with the chat there offstream. Next time the stream, I'm just gonna continue probably. Either I'm gonna continue with this list, verifying the list of solutions, or I'm going to try to convert micrograd from Andrei Karpathy to Rust. So see you next time.